Good morning. I hope you are having a wonderful day. If you took the exam yesterday, I am still on target for returning them to you on Friday. I've got another group taking them today, so I can't say much more. And if you are in Wednesday's class, and I don't think any of you are, then I'll take it. But anyway, so I can't say anything until Friday. So without further ado, let's go on to the next section. And we're going to kind of get away now from acids and bases, which is kind of cool. And we're going to look at our last major type of equilibrium constant. And we actually looked at this kind of equilibrium constant briefly in the Le Chatelier's principal lab. If you remember from that lab, we added some lead and chloride together to make like a solid. And one of the types of Ks you calculated was a KSP. And a KSP is the last like major type of K we're going to look at. It's really useful when it comes to determining how soluble things are, how fast they will precipitate, stuff like that. I do want to talk about some terminology I'm going to use just in case it's new to you or you haven't heard it for a while. A precipitate is nothing more than a solid, all right? So if you hear the word precipitate, it just means a solid. Sometimes I'll inadvertently use the phrase crash out of solution, and that means that a solid appears where there wasn't one before, all right? So if you hear that stuff, that just means that a solid is happening. And we'll also talk a little bit more about when things are soluble, which means they dissolve in water, and when they're insoluble, when they don't dissolve in water, and how you can make something insoluble soluble, and sometimes make soluble things insoluble. So without further ado, precipitation.
When a solution containing iodide ions is added to one containing lead 2+ ions, a precipitate of lead iodide forms. This precipitation reaction occurs because lead iodide is an insoluble ionic compound. Hydrated ions release water molecules and form the ionically bonded solid.
Initially, when you have an ion in a solvent, like water, which is real common, there's going to be usually some kind of ion dipole, intermolecular force. This is from Chem 222. It's a type of interaction between molecules in a solution. And the ion dipole force is fairly strong. However, after a while, lead and iodide really like each other, if you will. And so they're able to push the water out, and you end up then seeing, after not very much stuff has been added, this pretty intense yellow color. And this is lead 2 iodide. So lead 2 iodide has like a desire to form, and it's stronger than the intermolecular force of the ions, lead in this case with water, but you could have chloride with water. So they say that something is insoluble when the desire, if you will, for the ions to form solids is stronger than the intermolecular forces. And we'll see that. Now, in Chem 221, if you took that here with me or with somebody else, you were exposed to a table like this. And I'm going to refer to this table a lot in this section and stuff, and it's a good idea to kind of have a flashback reminder of how this works. And in Chem 222, when we wanted to know if something was a solid, all right, there were a lot of things that never made soluble, or that never made solids. And the big ones, in our case anyway, were sodium, potassium, ammonium, as well as nitrate, chloride, perchlorate, acetate, and stuff like that. And then if you wanted to see if there are any exceptions, then on this particular part of the table, this is where we look. So ones that we're going to start talking about a lot, and especially in this section, are when you have salts. An ionic compound is a salt. When you have an ionic compound with chloride, bromide, and iodide. And usually those are pretty soluble. So you can add them to water and stuff like that, and almost everything with chloride will be aqueous, soluble. But there are some exceptions. The silver, mercury, and lead ions right there, if they're in contact with chloride, bromide, or iodide, they will make an insoluble compound. And again, insoluble just means that you're going to put a little S next to it. It means that it's going to make a solid. So most of the time, chloride, bromide, and iodide will be aqueous when it's placed with other things. But with silver, mercury, and lead and stuff, that will be something that will be a solid. These ions down here in the lower left, all right, almost always do make insoluble compounds. And again, insoluble just means make a solid. But there are some exceptions. The alkali metals are the sodium, potassium, lithium ions, and ammonium. So for example, carbonate is almost always insoluble. It makes a solid really easily, but sodium carbonate, sodium is an alkali metal. Sodium carbonate would be an example of a water-soluble version. So here are three different compounds if you wanted to know if they were going to make a solid or not. And again, a solid means that it's insoluble. You would look up the different parts. So anything with nitrate is AQ soluble all the time. All right, no exceptions, at least so far. Chlorides are usually AQ, which means soluble, which means you wouldn't see a solid. The exceptions would be silver, mercury, and lead. On the other hand, down here, sulfates, I'm seeing it somewhere, where, there it is. Sulfates, most of the sulfates are soluble, AQ, but barium is an exception. So we wouldn't write BaSO4 AQ, we would write BaSO4 solid because it's insoluble. So again, just to get us all up to speed here, insoluble means a solid forms. Soluble means it's aqueous, you won't see anything. And a table like this is a rough way, at least, to figure out when something is soluble, when it dissolves, or when it's insoluble, when you'll see a solid. Any questions on this stuff? Okay. These rules work really well for Chem 221. They work really well for like the 100 series, but it's not totally accurate, all right? We're gonna see that there's a little bit more to it, and that's what we'll be exploring. So we're really gonna pull this table apart and see its value and its limitations as we go through this section. Now, sodium chloride is one of the examples on the last slide, always AQ, all right? If you look at sodium, always soluble. If you look at chloride, almost always soluble, except for silver, lead, and mercury, and sodium's not one of those. So we would expect to write NaCl AQ. But really what we should do, since now we've gone through equilibrium, is we should write it truly as an equilibrium. And notice how the solid is the reactant, and the ions that go into it are the products. This is very common in this section. The solid will be the reactant, and the ions that go into it will be the products. Now, if you've ever added sodium chloride to water, you can add a lot, all right? Keep stirring, stirring, and it goes away. But you will get to the point where you add just a little bit more, and then you start to see the solid.
When a small amount of sodium chloride is added to 100 grams of water, it dissolves. If we add more and more salt, eventually no more can dissolve in this amount of water. The quantity of salt dissolved in this solution, about 35 grams at room temperature, is a measure of sodium chloride's solubility in water.
So scientists like knowing when you get to the point where a solid forms, all right? And in sodium chloride's case, if you're adding it to 100 milliliters of water at room temperature, if you add about 35 grams of NaCl, which is quite a bit, that's when then you'll start to see a solid, all right? So little bits here and there, no problem. However you get to enough, it will do it. Now realize that in what I just said, there was a volume and there was a temperature, all right? The volume of water makes a big difference. If you have more water, you can dissolve more. On the other hand, temperature will also play a factor too, and we'll see that kind of stuff. So a chemist then can use solubility to predict when you will see a solid, and also conversely, you can figure out when you won't see a solid. Like if you want it to dissolve, you could go up to, you could add up to 34 grams per 100 milliliters apparently, and you would see just a solution. It wouldn't look like anything. And both of those things have use when it comes to chemistry. Excuse me. So if you have a solid formed when ions come together, in chemistry world we call it insoluble, all right? And really what that usually means is you see a solid, all right? You're seeing something happening. And it can happen in very dilute concentrations. It can happen in very large concentrations. Again, this is an example of what we're going to call the silver group. Silver, lead 2+, and this weird mercury 2,2+ ion all react really readily with chloride to make insoluble compounds. So if you had these three ions together and you added a chloride source, and that could be the NaCl we were just talking about, it could be HCl, something like that, all of those will make insoluble metal compounds, insoluble compounds. This is kind of a cool little high-speed thing that's been slowed down. We looked at silver chloride formation in Chem 221 in the unknown chloride lab. It's kind of pretty, I think, but it's also kind of neat to see how the different...
When moderately concentrated solutions containing silver ions and chloride ions are mixed, the resulting solution is supersaturated with silver chloride. A precipitation reaction occurs until the system reaches equilibrium. In this model, the red and white molecules are water. Chloride and silver ions, gray and green respectively, are in solution. When they encounter each other, they bond, and bind with other silver chloride molecules that have precipitated from solution to form the solid.
Remember that anytime you have a sample of anything, you're going to have 10 to the 23 atoms running around, or Avogadro's number. In this case, I find chloride something really interesting. Chloride, if you will, saw silver right away, and it made a solid, all right? So let's say that Justin and Hunter are great friends. Across the crowded room, Hunter, Justin, what's going on? And they see each other and stuff like that. Cool, all right? Sodium and chloride are quite different, all right? So we'll say that Hunter is chloride and I have sodium. I'm like, hey, Hunter, and he's like, hey, Hunter. Until finally, like, there's enough of me around or something that Hunter's like, okay, yeah, what's going on? So sodium and chloride don't have the same interactions, all right, that silver and chloride do. And in this case, it's really fantastic. Very small amounts of silver and chloride will make a quite obvious insoluble solid and stuff very readily. So the affinity for the ions is a really interesting thing. Some of them are really high, like in this case, and some of them you have to get a large amounts before they begin to make solids. And it's just it's a kind of an interesting part about chemistry. Now, if we rewrite this again as an equilibrium, all right, in this section, we're almost always going to have the solid as the reactant and the ions that go into it as the products. So in this case, it would be silver chloride solid as the reactant, and silver ions and chloride ions are the products. The thing about this, though, is that even in silver chloride, all right, two ions that like each other a lot, you have to get to some kind of a threshold concentration before they're able to see each other. Now with silver and chloride, it's pretty small, but if you keep adding water and water and water, it's going to make it happen. So this is an example, a little picture here, of what could happen with silver chloride. Like maybe this is silver and this is chloride, but they're too far away from each other, all right? There's not high enough concentrations of the ions to make it happen. However, when you do get to some kind of threshold where the silver and chloride do see each other, then you quickly, readily make the silver chloride molecules. This would be an example of an unsaturated solution. You do have some ions running around. This would be an example of a saturated solution. And saturated just means that the ions now are in close enough proximity that they begin to make solids. So your insoluble silver chloride will only happen in a saturated solution, all right? If it's unsaturated, you won't see a solid and no insoluble compounds will happen. So Once the equilibrium has been established, you're not going to see any solid until you get to the point of saturation. And that's another interesting thing here about solubility, is that you can have silver and ion concentrations, probably pretty low, but they can be pretty good. And then you'll finally hit like this threshold. I'm going to use this threshold idea a lot. Threshold where saturation begins. And then the ions will begin to form compounds and you'll see things happen. So for silver, thanks for playing, sodium chloride, all right? Sodium chloride is unsaturated a long way. It's like up to 35 grams per 100 milliliters, and that's a lot of solid added in. At that point, then finally the sodiums and the chlorides say, okay, that's when they begin to get saturated. On the other hand, silver chloride readily makes a saturated solution. You can see the solids right away. And if you dilute it though, or you have very, very small amounts of silver chloride, then nothing will happen and you'll have it unsaturated. So if you're going to have an insoluble compound form, you do have to get to the point of saturation, all right? And any compound, no matter how insoluble, if your concentrations are low enough, you can have it be unsaturated, where they do coexist, but they don't make solids. Cool. Questions on that? Cool. Now, people have studied silver chloride a lot. It was used in photography. There's lots of uses for it. They can remake silver metal if they want to. Anyway, when the solution of silver chloride is saturated, they've actually measured the concentration. Anything in square brackets will be moles per liter. So at the saturation point of silver chloride, it's 1.67 times 10 to the minus 5 moles per liter. Is that, based on the things we've done in lab recently, is that a pretty high concentration or a pretty low concentration? Low, right on. 10 to the minus 5 is really low. We were using like 10 to the minus 1 molar, roughly, concentrations in the last couple of weeks of lab. So 10 to the minus 5 is pretty small. So what that means is that if you've got chloride running around, you have to have at least this much silver to make a solid. If you were at 1.66 times 10 to the minus 5, you're going to be below that saturation point and you won't see a solid. On the other hand, if you get just a little bit beyond this, 1.68 times 10 to the minus 5, then you'll start to see a solid. And because this number is so low, that's why it's very easy to see silver chloride become an insoluble solid. The solubility is literally the measure as to how many moles per liter you can have before you begin to see a solid. So the threshold I keep talking about is really the solubility, all right? Like how much do we need before a solid starts to happen? And every compound has its own solubility, all right? Silver and chloride really want to form, so their solubilities will be really low. On the other hand, sodium chloride, you have to basically, kick it in the bottom and stuff to make it look at each other. That would have a very high solubility, all right, before anything happens. You got to basically force start that one. Now, because this is based on silver chloride, and silver and chloride are 1-to-1 here, the chloride concentration that is required for saturation will be the same as the silver, all right? 1 silver and 1 chloride come together. So if this silver would be 1.67 times 10 to the minus 5, that means the chloride would be 1.67 times 10 to the minus 5. If somebody asks you like how many grams are needed to make a solid in a milliliter of water, this is the kind of stuff you'll start with. You'll start with the solubility, which is usually moles per liter, and you can convert it over, and we'll talk more about this later. All right. So, if the silver and chloride ion solubility, the amount where you just get to the point where a solid forms, is that number, you can actually calculate an equilibrium constant, all right? It would be a K sub C, because C's means mole per liter. We would have products divided by reactants. Why did I not put silver chloride solid in the denominator? Solids, that's right. Pull the solids, pull the liquids out. So this K would be silver ion times chloride ion, or 1.67 times 10 to the minus 5 squared, or by itself. This K, 2.79 times 10 to the minus 10th. Now, using your understanding of K, is this reaction right here going to be reactant favored or product favored? Reactant. K is much less than 1, all right? And like all equilibria, if K is less than 1, you're going to have more reactant, which in this case is going to be the solid, and not as much product, which in this case is going to be the ions. So the Ks in this section, all right, the key solubility Ks, if they're small, which most of them will be, it means you're going to have a lot of solid. If you would happen to have a large K, then that would mean you'd have a lot of ions. You wouldn't have as much solid. All right. So 2.79 times 10 to the minus 10 is the product of the silver ion solubility and the chloride ion solubility. And so somebody thought, oh, well, it's like solubility of products, so let's call it a solubility product constant. Oh, joy. So KSP is the last major type of K we're going to look at. It's the product of ion solubilities. So you took the silver ion solubility times the chloride ion solubility to get this number. KSP is a type of an equilibrium constant. All of the KSPs, you write them as the solid, as the reactant, and the ions that go into it will be the products. So if you see a KSP that's less than 1, that means you're going to have a lot of solid. And although we won't see them probably, if you did see a KSP that was larger than 1, that would mean you'd have more ions around than you would have the solid. Okay. I wrote a guide for this section. I called it the Solubility Guide. It's in the companion. It's in the handout section. And if you have nothing else better to do with your time, and I'm sorry to even say that at this point, but if you do, check it out. I talk a lot more about where solubility is and what KSP means, and some of the examples and stuff will help and stuff there too. This is a table of KSP. So just like we saw Ka tables and Kb tables for acids and bases, there are tables of KSPs as well. And there's many different sources, and of course you could Google them and stuff. But what I'd like you to do is just look at the values here of KSP, all right? Almost all the KSP numbers, and the ones we definitely will look at, are Ks less than 1. So that means that you're going to have a lot of the product and not very much of the ions. So let's say, for example, you were curious here about the calcium hydroxide KSP. The equation for that would be calcium hydroxide, and it would be insoluble, so you'd write it as a solid. That would be your reactant. Then you'd write the equilibrium sign, and the products would be the ions that go into that thing. So in this case, that would be a calcium 2+ ion and 2 hydroxide ions. And the KSP that they quote there, 5.5 times 10 to the minus 5, that would equal the calcium ion concentration times the hydroxide ion concentration squared. So again, it's squared because there's a 2 right there. Nothing in the denominator since the reactant is a solid. This would be the kind of information you could take out of this number right there. And like all the Ks, you don't have to memorize any of them. I would give you those, or you could calculate them some way. We're going to do a lab after the class presentations on calcium hydroxide. So I'm bringing this one out specifically just to kind of preview what's coming up down the way. But again, if you saw a K less than 1, like this one, would you expect to have lots of solid or lots of dissolved ions? Solid, that's right. Remember, K is less than 1, always more reactant than product. We would expect to see a lot of solid in these kind of cases. So, any questions on that? Okay.
When solid lead chloride is added to water, a small number of ions are released into solution. Those ions can reattach to the solid, while other ions can dissolve. A state of dynamic equilibrium is reached, in which the concentrations of ions are constant and can be described by an equilibrium constant expression.
This is an example of adding a solid to water, all right? And this is lead 2 chloride, and the KSP 1.9 times 10 to the minus 5, and it's a K much less than 1. So you would expect to see solid form. But in reality, what's happening here is another equilibrium, all right? This is the solid lattice for the solid stuff. So these are little green ones are the chlorides, I think, and the silver ones are the leads. And you do see a lot of the solid there. However, some of the lead and chlorides are going into solution, all right? When water surround them like that, that's that ion dipole force that I was talking about earlier. So some of them do go into solution. Some of the ions up here will remake the solid. It's one of these back and forth kind of things, a true equilibrium, all right? Because K is so much less than 1, we expect to have a lot more solid than ions, but there are ions out there, all right? And because there's ions out there, we could do things to the ions. We could manipulate this expression by Le Chatelier's principle. So for example, if you added chloride, you'd make more solid. If you took the chloride away by adding silver or something like that, it would move the reaction to the right and you dissolve the solid. So equilibrium, all these Le Chatelier's principle things and stuff like that are going to come back to help us try and manipulate the expressions, making solid dissolve or making more solid appear. All right, so here's an example of a type of question you might see, all right? This is just a question where it says, I'd like you to try and find the equation that you would use for a KSP of barium fluoride, all right? So barium fluoride, barium is a group 2A metal, fluoride is a -1 nonmetal. So the formula would be BAF2. And if you want to write a KSP expression, it's like the one up here for calcium hydroxide. You would have the solid as the reactant and the ions that go into it as the products. So if you look through here, all right, let's go through these. This is showing that the solid is dissolving, and that's kind of cool, but it's not the KSP. KSP would actually have the ions right there. The second one I've seen once in a while, and that's why I wanted to bring it up. Fluorine is one of the diatomics, the have no fear of ice clear brew. But those versions only happen when you have neutral fluorine or neutral chlorine. And in a compound, you're going to have things that are ionic. So fluoride would be F -1. You don't see two negative ones coming together. So you only use the F2 part when it's neutral, when there's no positive or negative charge. So this one doesn't make sense. And then this one right here, you can see two Fs, 2F minus, a barium 2 plus, stuff like that. C would be the example of a KSP. This would be the inverse of a KSP, like you'd have this solid on the right side and the ions on the left. But for a KSP, you want the solid to be the reactant and the ions that go into it to be products. Any questions? So let's consider that lead to iodide example dissolving in water. It makes a really nice yellow color, which is kind of cool. And let's say that we've studied this reaction and we found that the solubility of this compound, 0.00130 moles per liter. So solubility in our context is going to be how many moles of the solid dissolve per liter. So this 0.00130 value, that's the moles of PbI2 that dissolve per liter. So in a liter of water, we'd have 0.00130 moles dissolved. In 2 liters of water, you'd have 0.00260 moles dissolved, stuff like that. But Solubility and KSP are different, and that's going to be really important, all right? A KSP is an equilibrium constant, and you can derive solubility from KSP and vice versa, but they are different numbers. So in this case, we've got solubility, we want to find KSP, no problem. Solubility again, how much solid dissolves per liter? All right, any compound, if you see the solubility, that's how many moles of the solid will dissolve per liter. So in this case then, the solubility, how many moles of the solid dissolve, that's going to equal the lead 2 plus concentration. And why I can say that, 1 mole of PbI2 makes 1 mole of Pb2 plus. So because it's a 1-to-1 ratio, the same number we had here is equal to the solubility of the lead 2 plus. If this is 1-to-1 and the solubility was equal to the lead, 1.30 10 to the minus 3, what do you think the relationship would be between solubility and the iodine? 2-to-1, yeah. You make 2 iodides for every 1 PbI2. So your solubility of iodide will be twice the solubility, or twice the lead concentration, 2.6 times 10 to the minus 3. Again, remember, if you see anything about solubility, it's about the solid, all that's said and done. So this number here says that you have 0.00130 moles of PbI2 dissolving per liter. And that happens to be the same as lead because of that 1-to-1 stoichiometry. And it'll be twice that number for the iodide, 2 iodides for every 1 PbI2. So this number times 2 will be the solubility of the iodide. Questions? Once you have the solubility, then KSP is literally the product of solubilities. So here's the lead, here's the iodide. KSP, lead 2 plus, which is going to be this number, times iodide squared. That 2 thing shows up 2 different places, all right? It affects the solubility, so it's 2 times the original solubility there. But we're also going to square it there. So one way to do this is you could take this number, the lead, multiply it by this number squared, which would be totally fine. But I'm also going to introduce the idea here, and you'll see why in a little bit, that because iodide was 2 times the lead, I can substitute in 2 times the lead for iodide. 2 squared is 4. Lead squared times lead would be lead to the cubed. Another way to think about this is 4 times the lead ion cubed. And remember that lead and the solubility are the same. So another way to think about this KSP, it's 4 times the solubility to the 3rd power. Now, there's nothing wrong with putting this number in there and this number squared, and that's totally legit. But when you're doing a lot of this, sometimes it's cool to have a relationship between the KSP and the solubility directly, and that's what I'm kind of leading up to here. So regardless of which way you do it, 4 times the solubility to the 3rd power, or this number times 0.0026 squared, either way you're going to get this number, which is the KSP for PbI2. All right, it's the solubility to the 3rd power times 4, or if you have it, you can do the lead concentration times 0.00260, the iodide concentration squared. Either way is fine. But sometimes it will be nice and stuff to think about it as a relationship between a KSP and the solubility. Let's call the solubility X. This would be an example where KSP equals 4 times the solubility to the 3rd power. I'll show you why this is kind of handy here a little bit. Questions on the math? Does everybody see where lead times iodide squared is essentially 4 times the solubility to the 3rd power? Is that cool? The reason why I'm introducing this is because tables of KSP abound. All right, they're all over the place. You can Google them right now. Solubility, though, is much trickier. Solubility is very specific. It can be temperature dependent and stuff like that. So the convention is that if you're working for the city of Portland and they want to know the solubility of lead-2 iodide, like when it starts to become a problem in their pipes or something like that. Neil, you'd have better examples than I can give here, but anyway, hopefully you see the idea. If they want you to tell it, they want you to tell them, there you go, how many grams does it take to make a solid? You're going to need the solubility X, all right? And finding the solubility can be a little tricky, but if you can find a KSP, you can convert KSP into solubility. So earlier on in the last example, we saw a PbI2, and the solubility X to KSP ratio would be you take the solubility to the third power and multiply it by 4 to get KSP. Anytime you have a 2-to-1 ratio of ions, like a 1 metal to 2 nonmetals, or like these ones right here, 2 metals to 1 nonmetal, it's going to be a KSP equals 4x cubed. So if you have the KSP for ammonium sulfite, which I have no idea what that is, and you were curious how soluble it was in moles per liter, you would solve for X, all right? That's what you would do. If it's 1 cation and 1 anion, so for example, potassium and chloride, or sodium and chloride, you can turn your KSP into an X squared by this relationship, KSP equals X squared. These first 3 are ones we're going to look at a lot. If you had other ones, though, it's no problem. I'm throwing them up here more just to impress your friends and parents, I don't know. But anyway, this is an example of 3-to-1, so like 3 metals and 1 nonmetal, or 3 nonmetals and 1 metal. KSP equals 27x to the 4th. So you could find KSP from X or X from KSP. And these crazy things down here, which are less common, they would have either 2 metals and 3 nonmetals, or 3 metals and 2 nonmetals. And you can use this kind of stuff. So again, if you go into an environmental setting, solubility, as we're going to see, can be pretty helpful sometimes. You can look up KSP easy on Google, and you can translate it to the solubility, how many moles of that compound dissolve per liter. Let's look at some examples. This is a copper 2 phosphate, and we looked up the KSP 1.4 times 10 to the minus 37. So K less than 1 means we have a heck of a lot of solid, not a lot of ions. But your boss, or you're just curious, you want the solubility, which is how many moles of the compound actually dissolve per liter. So one thing we have to know, of course, is the formula. So copper is a +2, and phosphate, a polyatomic ion, PO4 minus 3. So when you figure out the ratio, this would be Cu3, PO4, 2. We need 3 positive 2s to balance the 2 negative 3 ions that are present. This is an example of having 3 metals to 2 nonmetals. It's one of those 108 to the x5th kind of things. We're after the x part of the x to the 5th. So what we can do then is put this KSP right there and solve for x. So I'm sure you're all dying to know what that number is. KSP divided by 108, take out the number first. You take it to the 1/5 power. This would be like taking a square root, but the 1/5 square root. And mathematically, you can use that little caret symbol and then parentheses 1/5. The solubility of this crazy thing, 1.7 times 10 to the minus 8. So what that means is that copper 2 phosphate, if you put in 1.6 times 10 to the minus 8 moles per liter, no solid forms. But 1.71, just a little bit beyond this number, that's when you'll start to see a solid. And again, this is very insoluble. That's a really small number. So copper and phosphate are going to run to each other basically once they figure it out. If you don't want them to run to each other, keep your ions like under that level. Now, sometimes you have solubility and you want to turn it into KSP, and that's something that happens too. So let's say we're studying magnesium carbonate, MgCO3, and we want to figure out what its KSP is. So we figured out this number, that it takes 2.6 times 10 to the minus 3 moles of magnesium carbonate in a liter to start making the solid form. But we want the KSP. Well, solubility for a 1-to-1 compound, 1 positive to 1 negative, its KSP equals x squared. And this number literally is the x. So if you take that number and you square it, KSP here, 6.8 times 10 to the minus 6. So, yeah, go ahead. What is CO3 called? What kind of species is it? The what? Carbonate, yeah. It's a polyatomic, Margaret. And if carbonate is something you haven't seen, just look back at the table, and I can send you one, okay? But carbonate usually sticks together, all right? It's CO3 negative 2. It's not just carbon, and it's not just oxygen, it's the mixture. This hydroxide is another example, and phosphate would be another example. So yeah, so prop that off, all right? We're seeing some stuff from Chem 221, and if you're like me, I don't even remember what I had for breakfast this morning, so if you're having questions on things like polyatomics and stuff, I can send you a list of tables and stuff with this kind of stuff, so good. These are good questions. Prop that back on. Yeah. Okay, maybe not big. All right, so here's an example. We have a solubility of barium sulfate. Does anybody remember what the formula for barium sulfate is? BaSO4. Well done. BaSO4 is the formula. So BaSO4 is going to break up into barium 2 plus and sulfate ions. And like Margaret asked about, sulfate is another polyatomic. It's SO4 minus 2. But what you need to solve this is that this is a 1-to-1 compound. It's barium 2 plus times sulfate, and we have the solubility. That's the part that goes in the barium and the sulfate. So this number times itself, or this number squared, this would be KSP equals x squared, and we have x. You're going to get 1.10 times 10 to the minus 10. So solubility squared is how you'd find KSP. You could also take this and multiply it by itself. Again, very, very small KSP numbers. KSP, we're going to see, has a lot more uses than just solubility, so that's why KSP values are usually listed. It's easy, I find, to find the KSP values, but it's more difficult to find solubility. So, Gesundheit. Any questions? Okay. Here's another kind of question that you might run into. Mercury is a pretty nasty compound when it's let loose in the environment. Lots of weird things it does. So let's say that we have a bottle of mercury sticking around and we want to kind of get rid of it, all right? Getting rid of it, in my world, usually means that you make it into a solid. The solid can be dried, all right? We put it in a special container, and usually it gets shipped to a place like Umatilla, Oregon, where they have apparently a huge depository where they bury this kind of stuff. I'm not going to say it's wrong or right, I'm just saying that's what it means. So prop that on, off, I'm not sure anymore. But anyway, if I wish to get rid of something bad in a solution, what I usually do is I make a solid out of it. I then give it to the stockroom people who send it somewhere, which is probably scarier than what I had. But anyway, we'll prop that back on. Getting rid of something means making a solid. So in this case, we've got mercury 2 plus ions rolling around, and we want to add chloride to make the solid, to get rid of it, to send Umatilla where it's environmentally, oh no, sorry, I'm not going to go down. Anyway, we're going to make it into a solid. How much chloride do we need to begin precipitating out this ion? All right, so we want to make the ion a solid. That's really what this comes down to, all right? And we've got 10 to the minus 2 molar, which is fairly concentrated. But knowing that Hg2Cl2 forms a solid readily, we can make this happen. This is a weird diatomic cation, by the way. There's weird reasons why mercury's d orbitals mix together and make this. And that's kind of beyond our class, what's happening there. But just realize that this is a very common form of mercury. Anyway, the question at first comes, well, we've got a KSP here value. And we don't want to find the solubility necessarily because we already have some mercury present. But what we'd like to do in this case is solve for the chloride. So if you just look at this number, KSP, this number, equals mercury times chloride squared. And if this is the concentration of mercury, we'll put it right in there. We're essentially going to solve for chloride ion here in this expression. So when we're going to do mathematically here isn't too hard, but what we're really asking is what is the maximum chloride that can be in the solution, that 10 to the minus 2.010 molar mercury, without actually forming the mercury, all right? How much does it take to just begin to see a solid crash out, to see a precipitate form? And we can do that with KSP. Because KSP is really great about determining these equilibrium solubilities and stuff. So again, mathematically what we're going to do is we're just going to take this expression, we're going to put that mercury number right in there, and we're going to solve for chloride. And that will be the threshold of chloride needed to begin making Hg2Cl2. So again, mathematically it's not too bad. KSP is literally the product of the maximum ions you can have before you begin to see solids, or after that you will begin to not see solids. And we're going to find a number here pretty soon, which is the concentration of the chloride. And once you get past that number, that's when the KSP, you go past it and you begin to see a solid. So this whole threshold thing I keep talking about, we're going to find the threshold of chloride needed to make a solid. And numbers under that threshold, no solid. But numbers just a little bit above that number, we will see a solid. So, if the concentration of the mercury is 0.010, and we place it right there, we're going to solve for chloride. And chloride squared equals KSP divided by mercury. The square root of KSP divided by mercury will give us the actual chloride. And you can see here that the concentration that comes out, 1.0 times 10 to the minus 8th moles per liter. Is 10 to the minus 8th moles per liter a big concentration or a small concentration? Small. Chloride just kind of has to look at the mercury and a solid begins to form. That's a really small number. Again, most of the time in lab, 10 to the minus 1, 10 to the minus 2 moles per liter. This is 10 to the minus 8, so it doesn't take hardly any chloride to have happen. On the other hand, if Alyssa and I really don't want to have a solid, but we want to add chloride, we could make a solution 0.9 times 10 to the minus 8th, just a little bit below this number, all right? And if we added that to this amount of mercury, we wouldn't see a solid. But what's probably going to happen with dilute concentrations, we would accidentally add extra and we would see a solid. But in theory, 0.9 times 10 to the minus 8th, just a little bit below that, no solid. 1.01, just a little bit above this, start to see a solid. Okay, that is the threshold between not seeing a solid and seeing a solid. Oh boy. So, KSP, in this problem, now we're going to ramp up the chloride. We're going to raise it to 1 mole per liter, which is a much more reasonable lab value. And the mercury was at 0.01. It'd be kind of fun to know what the mercury is now at our new concentration. So we're going to go back to the idea that KSP here equals mercury times chloride squared. And in this new context now, chloride is 1.0 moles per liter. So we're trying to figure out the new amount of mercury. And so what you can see here, we're going to solve for the new mercury. KSP, our chloride squared, 1 squared. Whoa! Mercury went from 10 to the minus 2, which is what we started with, to 10 to the minus 18th. All right, that's a change of 10 to the 16th or so. That's a very, very, very large amount. So most chemists would feel that you've basically got the mercury out. All right, 10 to the minus 18th is pretty freaking small. However, did we really get all the mercury out? No. There's always going to be a little bit of stuff left over. You have to decide as a person, as a scientist, as a politician, as a voting member of society, is this a safe amount? All right? Because there's always going to be it. There's really interesting history in the last decade or so of what safe arsenic levels are. Now, arsenic is like mercury to me. It makes me kind of nervous. But some people, in order to keep costs down, they think, well, you know, we can raise mercury, arsenic from like 0.1 to 0.5 or something like that. Safe? I don't know. These are things that you can start thinking about now as a scientist. Like, what is a safe amount? Okay, we're going to do more of this on Friday. Have a wonderful day. I'll see you guys later.